Hey, we're here with Victor from Icengineworks, and today we're going to be working with the 1 3/4 modeling block set to build a kind of a standard setup for a header. We're going to be using 2 and 3 inch centerline radiuses. So, Victor, if you would give us a little bit more explanation on what's in a kit when you buy it, and kind of what we're going to be working with here today.
Yes, well, as Bryson said today, we're just going to give a quick overview of how we work the system, how we use Icengineworks to develop a quick design. For this particular exercise, we're going to use 2 and 3 inch center lines, simply because of the fact that we have a kind of like a limited space. And we're starting presenting how the block sets come in. They come in a plastic case. And they include instructions, they include bags of different types and shapes of blocks, and block adapters, which are the little plugs that we're going to use to attach the blocks to the flanges with the starter tubes. So let's get started.
All right.
So as our original plan, we're going to use only 3 shapes. We're going to use the straight block. We're going to use a 2 inch centerline radius block and a 3 inch centerline radius block. So the first thing we're going to do is make sure we got a flange already with starter tubes, a solid location for our block, so we can start connecting it to our desired location in the collector dummy. You can use also a regular collector or a slip type collector, depending on what you want. We developed this part simply to ease the trouble of having to find the right location and create a solid fixed point B, where we're going to be landing and exercise, reviewing our design. So first thing is attaching the blocks. We're going to pick, which shape do you think you might do? Let's do
I'd say start with
this one.
There, yeah.
So we're picking a 3 inch centerline radius block. The procedure is very simple. These things just slide in. And we got to make sure that they are flushed. So the way these work is when you tighten the bolt, the rubber discs will expand. And in the case of the one over the block, it needs to expand the rubber side over the block. So if it's not properly flushed, it will expand right in the middle of it, and it will crack it. So we got to make sure it's past that and it's flushed. And then we just simply insert it, and then tighten it until the rubber starts expanding. These are designed to work anywhere from 18 to 16 gauge metal, assuming, of course, the tubing is precise. Unfortunately, we've noticed that out in the market there's tubing that says 1 3/4. In this case, for example, it measures 30 thousandths, 40 thousandths over. So you got to make sure that it's a quality product. In cases like that, it's very simple just to put anywhere from aluminum foil to masking tape, just to create more of a shim. Just simply that this thing can grab on the inner walls of the tube. But now that we're ready, from this point on, we can start plugging in blocks as we desire, and we start creating our shape. The reason we developed this is because when we use this type of collectors, the form collectors, these are made out of a cone that is just crimped. Usually the precision is not exactly there. There's a lot of leeway, which in a way is good. It helps us, but at the same time it creates the problem of having it's very difficult sometimes to actually line up the tubes. So we created this as a template to make sure that all the tubes that go in here, first of all, will be parallel, and that will simplify the welding. And just to give you an example, if we put this here, there's again all this motion that is very difficult when we try to weld it. Also aesthetically, it looks terrible, So we like to have them nicely parallel, and this also helps in the flow because we have more of conserve more of the energy of the flow in the same direction. So these guys plug in all the way in here, and they are perfectly parallel. So the whole idea is once we design with these things, they have a common stop, so they're flushed. Eventually, when we develop the metal version, we will we're replacing this with metal sections, and they will end up at the same point. And then when we're ready, when everything is welded, we can remove this and simply just slip on the actual collector and then just tack it. That's really the advantage of this thing. The alternative is to use this there, but as you can see, it's very difficult to locate it, to put it in a firm position without really damaging the finish. We'll have to tack into this and then later clean it up. That's why we develop these things. In theory, you can put this anywhere you need around the engine, whether you're shooting in the front, you're going up, you're going down, anywhere you want. You just create the braces to hold this. You can do anything to these things. You can bolt them, clamp them, tack them, anything you want to do. You can be ugly to these things. They're made out of 12 gauge 304. They can always be cleaned, but you will always save the finish of your collector. So with this in mind, now it's really a matter of connecting point A to point B. And of course, we have a lot of options. This is really one of the benefits of our system. It gives you a lot of options to be able to review which one is the best. We can put this cylinder on this quadrant, or on this one, or on that one, or and then we can go this way, we can go that way, we can play with the firing order. There's so many options, and that's really the whole point of using this system. So, Bryson, if you want to do the honors and start laying out something, we'll just play along for a little bit. It doesn't really take a long time to develop something, even if you're a first-time user. Our experience with some of our clients, within 30, 40 minutes, first time around, you're able to create a full system on a bank, on one side. And that gives you a very good idea as far as how to start improving from that point.
So what are each one of the blocks, what are the lengths of the blocks and what they represent?
That's a very good question. What we did on the EH series, exhaust header series, is give each block exactly 1 inch at the imaginary arc length. And the reason is we're interested in performance. We want to know that we can tune a header exactly to a length that either our dyno experience is telling us, or engine builder is telling us, or simply we just want to choose a certain length. So what we did is we gave every block exactly 1 inch at the center line. So to create, for example, a 22-inch header, we just need to count 22 blocks, regardless of their shape, making it to the same point. And then we coil them and package them in such a way that they fit. That's really the whole purpose. All the engineering, all the science of how to make a header tune is out there. The challenge for always has been how to package it in the available space. So that's what we're trying to solve with our system.
Sounds good.
So,
all right.
Well, Bryson works. I'll explain a little bit of the philosophy or the design guidelines. Every block is molded with some markings that are very helpful for the design. The most important one is the arrows at the very top of it. When those arrows are aligned and you're using the same centerline radius, we are actually saving ourselves a lot of work, because this means that all this section can come out of the same U-bend. So the more blocks we're able to use of the same type, the less work we want to do, and that's what we want. We want to produce the best performing header without really having to spend a whole week building it. So, like he's doing here, in this case, we're trying to connect as many of the same type to be able to lessen the amount of work, and at the same time create the shape that will fit in the allocated space. Another thing important in our design is these arrows also signal that every time there's a break in their line, we need to create a new section, which means we need to have a cut and a weld. So when we're designing, and we keep that in mind, we try to avoid situations like this where we have different changes in planes, because this means a lot of cut and a weld, a cut and a weld, and a cut and a weld. If we go back and review our design and start cleaning this up a little bit, it will take us literally minutes, if not seconds. We're saving ourselves hours of work, hours of cutting, hours of welding, and that's really the whole point. pretty clean.
Look at that.
Pretty clean. So in this case, Bryson was able to fit the whole thing in without really any gap. Sometimes there's a little bit of an issue. Obviously, we're rounding it up to the next inch, but sometimes it's just simply making it up. You know, you may have a little bit of a 1/4 of an inch gap or an 1/8 of an inch that can easily be made up when you're cutting your metal. So it's still a relatively imperfect method, but it's very close to the real thing, because we're still human. We're still having inducing a lot of human error. But yeah, in general, I mean, this took what, 3 minutes probably to build, layout.
Something like that.
And again, if there's anything in the design that we don't like, we can always go back and change it. And again, it will take 3, 4, 5 minutes to find another solution. So all these layouts, all these different designs allow us to evaluate the criteria that we are trying to put into our design, whether it's performance, regardless of the work, whether it's just creating a quick solution that won't take too much time, or create something that is extremely good looking and appealing, maybe for a show car. So everything can be worked with this, just as long as you have your mission set as far as what the purpose of the design is. So all right, you want to move to another one?
Yeah, let's keep building.
Right.
Bam. So it only took us about 15 minutes to get to this point here, to where we're now ready to transfer the modeling blocks over to converting it into the actual tubing. So Victor, you want to explain to us a little bit of how that happens?
Yes, so Bryson just finished what we call in our system stage 1, which is the modeling and design. He got the shape, he got all the features he wants, length, etc., the layout. And then now, as he mentions, we're ready now to move on to stage 2, which is the cutting of the metal sections to start replacing. So completing section 1, stage 1, we're going to fill out the control sheets. These are really the brains of the project, because they will allow us to download all this information into a practical data that we can use as a shopping list, and also to budget, and also to create ultimately the final cost of our project. So following with that, again, all that information is included in our instructions. There's all the design guidelines that we suggest to work this in a quick way. Bryson did a pretty good job, taking less than half an hour to build this. So imagine the possibilities. If you allocate 2 or 3 hours to do this, you will have the opportunity to review several layouts and be able to zoom into the one that is the most effective. Again, depending on your criteria, least amount of work, the best shape, the most performing in terms of length, whatever is your choice. So again, from this point, we're going to start just to show how it's done. We're going to use this first runner, and we're going to start off with how many blocks do we have of each one. And again, based on our design guidelines, we're following always the line that the arrows create when they are all together. Can be one section, of course, assuming this is the same centerline radius, which is. But this is something we always make sure. It's a quick verification of every block being lined up properly, making sure we're not by mistake mixing one of the different types, because I've done that. So this all seems to be ready to go. So we're going to start tallying.
Yeah, we have 4 of the 3-inch.
4 of the 3-inch. Now we have a choice here. We can leave this. It's already welded, so the start to. That's another possibility that sometimes can be included in the first section, just to have one less weld. In this case, it's already ready, so we're going to take it as it is. We're just going to start adding from here. how many you count?
4.
4 on 3-inch radius, right?
Yep.
So we're going to go to our control sheet. In our control sheet, we essentially have broken up the shapes of the bends based on the centerline radius that we have available. So in the case of the first one is a 2-inch centerline radius, which is this one, and that can fit 6 blocks, and then the straights, of course. The next one is a 3-inch, which is this one. That can fit around 9 blocks. And then there's a 4, there's a 6 that we didn't use this time. But so considering this is a 4-inch, on 3-inch radius, we're going to pick our 3-inch radius center line, and we're going to mark off 4 blocks, 1, 2, 3, 4. And then we like to color these just simply to make them stand out and we don't get confused. Crayons or markers are really an easy way to do this. So that's our first section. We like to create a system so we don't get confused with the numbers. If we assume that this is cylinder 1, we're going to call this 1, 2, 3, and 4, and we like to choose letters for the sections. So we recommend doing that. So the first section would be, in this case, would be section 4A, which is cylinder 4, section A, and we're going to make a marking here, labeling it. We want to mark the direction of the flow in the part because this will become very important later on when we have sections that actually combine a straight section. So we don't, when we're welding, we don't flip them in the wrong direction. In this case, because it's the same, it's symmetrical, it doesn't really make a difference. However, we still do it just as a matter of habit. So that's our first section. In the case of the EH series, and I recommend this as well, to keep track of lengths, I also add this value to that section. That is, this is worth 4 inches in parentheses. So what we can do later is actually have cylinder 1, cylinder 2, cylinder 3, and cylinder 4, and then tally exactly their lengths. So the cylinder 4 has 4. We're going to move on to the next. The next one, how many do we have, Bryson?
It's like 4 before
4
we have
up
a
to
break
here. Okay.
of the 2-inch center line.
Okay, so that would be section 4B. And so we're going to now use another 4. We still have left in this U-bend. And this is really...
It'd be the 2-inch center line,
Oh,
right?
sorry,
Yeah.
it's a 2-inch. Okay.
Yeah.
Good catch. So 1, 2, 3, 4. And this is a 4B. And again, because it doesn't have any straight end, it can be either way, but still we're marking a flow in one direction. And then again, the length, it's 4 inches. So on our cylinder number 4, we're adding 4 more inches. This is cylinder 3, cylinder 1, cylinder 2. And then we're going to color this yellow. Now, this is something that it's worth pointing out at this point. All these drawings have a little bit of a wedge left there. This has to do with the fact that because of the formula for perimeter that uses pi number, which is an ugly number, 3.14, if you work the math as far as what is the actual length of this, in the case of the 2-inch, you will see that the number you will get is around 6.42 inches. It's essentially pi times times the radius. Because we're working in whole inches, we only take the 6 part of the 6.14, and the 42 we just left it. Leave it out, which is exactly this section. So what this means in practical terms is that by putting 6 of these, we cannot do 180 degrees. We'll do something short, 172, 171. But it doesn't matter because what we're after is the length. Now, some people might think this is a problem when cutting, but the reality is not, because the system will tell you exactly where to cut, and it doesn't matter the angle. You know, whether it's a 19 degree or a 20 degree, it doesn't matter. You just make the cut where it tells you, and that's really the beauty of this product, because it has no exact numbers, no things that require measurement. So that's 4B. The next one, what would be?
Looks like we have, it's a 2-inch center line. We have 3 on the bend and then another 3 out on straight.
Okay. So this is an interesting case because here we can choose, and this is actually laid out pretty well, because we can choose where to put this bend. I mean, this straight section, we can put it on this bend or on that bend, but of course we have another one here. So to make the design cleaner and save on welds, we can create this, so as you said, all this one section, put a well here, and then this is another section over here. Instead of, sometimes what we see is redundant welds. They make a weld here, another one there, another one there. We don't need that. That's saving us 40 minutes probably.
Mhm.
So this is this is the next one. 1, 2, 3, and 3 inches straight. So again, we go back to our 2-inch centerline radius. Bends. We only have 2 left here, so we got to use a new one, and that's going to be 3 inches. So we marked 3 inches, and it's going to have 3 inches of straight. So 1, 2, 3, 1, 2, 3. So this is our next section. And again, we color it just to make sure we don't, that material is already used or taken. And we label this. This is now going to be 4C. Now, in this one, this is when really the arrow for the flow becomes important. We're flowing from the bend into the straight. And then again, this is worth 6 inches long. So we add that to our length now. And then we're ready to move to the next one, the last one.
Yeah, so we have a 3-inch radius, just one, and then 4 straight.
4 straights, okay. So 3-inch radius, we have a lot of material here left. So here, for example, we have a good choice. We can either switch this to this side, or we can ignore the gap, the little wedge here, and just take the hole as a full, and then add 4 inches. 1, 2, 3, 4. So that will be our next and last section for this cylinder. That is section 4, D as in David. It flows from the bend into the straight, and this is 5 inches long. We add 5 inches long here, and here this is when the magic starts happening, because now we know that this runner is 19 inches long. And of course we need to add this one as well for all practical purposes as far as resonance and tuning, but at least the runner requires 19 inches. Now we're going to do this for the rest of the project and be able to fill this out to create a whole shopping list. But essentially what will end up happening is that for us to build this part, we need 2 U-bends of the 2-inch centerline radius and 1 of the 3-inch centerline radius. And again, that allows us to put a price tag to this runner. It also tells us that for every section we need to make 2 cuts. So we have 1, 2, 3, 4 sections. We have 8 cuts to make, and we have 1, 2, 3, 4, 5 welds eventually. And now again, all that is cost that takes no time to figure out. So I know that to produce this runner, I need to buy 3 U-bends, I need to make X amount of cuts, X amount of welds, and have a total for that. And it took us 5 minutes to do this. This is really the beauty of it. If this number is too ugly, takes too many welds, too many cuts, too many U-bends, then we can rearrange it and start narrowing it down or making it more efficient. This is really the power of these blocks. And after that, we're ready to go. So if you're okay with it, I guess now we can jump onto stage 2 and start sectioning our U-bends to replace with the metal parts.
Sounds good. All right, well, we got all the parts cut for this first runner on this, and so at this point now, what's the process for taking it and actually tacking it together?
Okay, so Bryson really spent literally minutes, half an hour probably going through all these, and it's so quick. Anyway, so now we're going to label these things just to make sure that we're on the right track for each one. We start with 4A, which is 3-inch centerline with 4 blocks or 4 inches. 4B is going to be 4 inches on 2-inch centerline radius. Of course, nice job already getting rid of all the flash and the bearing, so it's ready to be welded. 4C, 2-inch centerline radius with a short leg, and then flow from the bend to the straight. And finally 4D, 3-inch centerline radius, 1 block, and then 4 inches of straight, also flowing from the bend to the straight. So at this point, this completes stage 2 cutting. Now we have all the parts of the puzzle, and now we're ready to put it together. For that, we're going to use our proprietary welding clamps, which really constitute the stage 3, as we call them. Assembly and welding, we call that part. And before we do that, we want to make sure, first of all, we're going to be welding circle to circle. So sometimes in the bending process, depending on the supplier, there's a little bit of egging on the circumference, and this has to do with a lot of things: the wear on the tool that is actually doing the bending, the quality of the tubing, you know, where the seam is located along the circumference. So again, we want to make sure that we're welding circle to circle, because otherwise we're going to have gaps that can create, you know, we can actually blow a hole through it. So the only one I can see that we need to just touch up a little bit, this one is a little leg, as you can see, it's a little wider on this side. So we just put on a vise very gently and just kind of restore the circle. And on this one is the same thing, it's a little flat on the top. So let's work on that, and then we can start connecting them and setting it up. Alright, so now we're ready, Bryson, to start putting it together. We got the circles recovered, and so essentially what we'll do is try to replicate it by following this is our master, really, just following those bends and try to mimic them as the best we can on the outside. And then eventually what we will do is replace that section, and then the actual metal, when we'll be tweaking the joints until the goal is to get gapless joints that are concentric, so we can come back and just stack them all at once. So the way our clamps work is that there are 2 different motions. There is this what we call the adjustable link. It has a fixed point, and then it has another one that is the one that is adjusted. So this first ring is going to be the one that dictates the angle, the rotation relative to the tube. And this other one is one that creates the arc of the joint that we want to create. So we recommend putting this one on the most straight of the bend, the most straight of the 2 joints that we want to put together. So in the case of, we're going to use a 3-inch joint to a 2-inch centerline radius of the first part, 4A and 4B. So we recommend putting then first the solid part, the bottom ring on the one that is most straight, and then we put the one that arcs out to the tighter of the other ones, the tighter of the other tube. So then what we do is actually try to put this in the middle. And then the trick to make this gapless is by finding the highest point of each tube, which in this case is this one, and then placing this in between. When you are able to do that, then you close the gap. If it's off, then what we have is issues like this. So again, finding the highest point of each of the sections and then placing this link in between those 2. This is explained obviously in the instructions. So at this point we can just kind of tighten it gently so we can still rotate it. Another tip is the closer we can have the rings, the better. It will be a lot easier to control the spacing. So like this, we start building it, and then, for example, we're off. Now we're able to just gently rotate it and start getting closer and closer. So now the next section will be this guy, and I don't know if you want to do this one, Bryson. So now Bryson got it all put together. Now we're facing sometimes a possible scenario where we could actually continue with this, and in order to be able to fit it, we would need to remove some of these, which we can do, or another because the problem we're going to have is interference. Obviously, the clamps, as compact as we try to make them, they do occupy space, and sometimes on tight situations there won't be room enough. So here we have a couple of options. We can either remove this runner, which is only one, that's very doable, or the other option is actually to remove the clamp, play with this the way it is, put this clamp here so we can clamp it to this point, and then use this and just tack this by hand, which is only one joint. That's not really that bad. We put a tack on it, and then we take off the whole thing, and then we can tack it all. Whichever way you prefer, Bryson. I mean, as I said, we can take off this part, and that should be able to do it.
I say we leave that on there, and we can get the top section in here and kind of get it fit in.
All right. Well, let's do that.
All right, well, we got the runner here clamped in place, got a few tacks in here to hold it, so you can see how quickly you can go from the molded part to actually having a part in place, and then from there it'd be obviously just continuing those same steps onto the other runners. So any final thoughts, Victor?
No, I think you've done a great job just showing how simple it is. It's very methodical. Our philosophy has always been to break the entire process into little steps that are more precise to control, and the result is a fast, efficient, and precise end product like you're showing. So, thank you for looking into this. That's it. I mean,
yeah,
simple as that. Have fun with these parts.
Well, if you're interested in the Icengineworks products, visit our website at tricktools.com. Give us a call, and we can help answer any other questions you may have. And thanks for checking out this video, and subscribe to our YouTube channel for more videos on high performance tools for the fabricator.